When you apply an input torque to a Rohloff Speedhub through the sprocket, there's an output torque through the hub shell to the road. There's an additional output torque through the torque arm, which has to be resisted in order for the hub to provide forward drive. Depending what gear you're in, there's a different amount of torque that goes through the torque arm. What I'm interested in finding out is how much torque goes through the torque arm in the different hub gears for a given input torque through the sprocket. I'm going to set up an experiment to try and work this out. This is what I've come up with. I've got a G-clamp clamped to the disc, and when I apply an input torque to the hub, the G-clamp rests up against the chainstay, and that resists any output torque that would normally be going to the road. I've also removed the quick release, so there's no clamping pressure being applied to the axle. I've got this 5 kilo weight, and what I'll do is I'll hang that off the pedal, and that will apply a known input torque to the hub. And then what I'll do is I'll attach weights to the end of the torque arm using this piece of rope, and the aim is to get it so that the torque arm and the crank are perfectly balanced. If there's too much weight on the crank, the torque arm will lift up in the air, and if there's too much weight on the torque arm, the crank will lift up in the air. So the aim is to get this perfectly balanced. Instead of just doing this by trial and error, what I'm going to do is I'm going to calculate how much weight we need on the end of the torque arm for each gear. To understand what force is needed at the end of the torque arm to resist the input torque to the hub, we need to understand what torque is. So let's take a look at that. The torque T is equal to force F times distance D. Let's look at an example. If we have a fulcrum or a point of rotation with a lever arm on either side of it, let's give this lever arm a length of 0.5 meter, and we'll give this lever arm a length of 1 meter. If we have a force here of 50 newtons, we can work out the torque about this fulcrum by multiplying 50 by 0.5, which gives us a torque of 25 newton meters. If we want to work out what the force is at the end of this lever arm, we need to rearrange this equation for F. So it becomes F equals torque divided by distance. So in this case, it would be 25 divided by 1, which is equal to 25. So the force is equal to 25 newtons. And of course the force is in the opposite direction to this force. Now that we understand that, we can take a look at the hub input torque and the bottom bracket input torque and how we work them out. So first of all, let's look at the bottom bracket. We can draw the bottom bracket with the crank and the chainring and the sprocket and the chain which connects them. We know what length the crank is. It's 0.175 meters. We know what the force is at the end of the crank. It's 5 kilos, which is 50 newtons. So the torque about the bottom bracket is 50 times 0.175, which is equal to 8.75 newton meters. We know how many teeth the chainring have. It's 36. We know how many teeth the sprocket has. It's 16. So the ratio between the chainring and the sprocket is equal to 36 divided by 16, which is equal to 2.25. And what that means is, for one revolution of the chainring, the sprocket rotates 2.25 times. So we have a speed amplification between the chainring and the sprocket. If we had a torque amplification between the chainring and the sprocket, the chainring would have to be smaller than the sprocket, which would make this value less than 1. We can use the input torque to the bottom bracket and this ratio to work out the input torque to the hub. We simply take the input torque to the bottom bracket of 8.75 and we divide that by 2.25, and that gives us 3.89 Newton meters. It's important to understand though that no matter what gear the Rohloff hub is in, 1 through 14, the input torque to the hub is going to be the same at 3.89 Newton meters, because we haven't changed the weight at the end of the crank or the ratio between the chainring and the sprocket. Now that we know what the hub input torque is, we can use this to work out what force is needed at the end of the torque arm to resist the input torque to the hub. Set up this table, and in this column we have the Rohloff gear number, and in this column we have the Rohloff internal gear ratio for the corresponding gear. So you can see that in gears 1 to 10 we have internal gear ratios of less than 1. In gear 11 we have a gear ratio of 1, and then in gears 12, 13 and 14 we have ratios that are greater than 1. So in gears 1 to 10 we have a torque amplification, and in gear 11 we have a direct drive, and in gears 12, 13 and 14 we have a speed amplification. So where we have a torque amplification, the sprocket will rotate faster than the hub shell. In a 1-to-1 direct drive, the sprocket will rotate at the same speed as the hub shell, and with speed amplification the sprocket will rotate slower than the hub shell. To fill out this column, torque to road, we need the hub input torque and the internal gear ratio. So we know what the hub input torque is for each gear. It's always 3.89 Newton meters. We know what the gear ratio is. So to work out the torque to the road, we simply divide 3.89 by the internal gear ratio. So in gear 1, that's 3.89 divided by 0.279, which gives us a value of 13.94 Newton meters. So we can do that for each gear and populate this column. We know that the hub input torque has to equal the hub output torque, so we can use this rule to work out the reactionary torque to the frame. If we set up an equation with the hub input torque on one side and the hub output torque on the other side, we know that they have to equal each other. So the hub input torque was 3.89 Newton meters, and that must equal the torque that's going to the road, which is 13.94 in gear 1, plus the torque to the frame. Let's give that a value of x. So if we want to work out the torque to the frame, we need to rearrange for x. So x becomes 3.89 minus 13.94. So x is equal to minus 10.05 Newton meters. So we can put that value in our column and we can populate the rest of the column. Now that we know what the reactionary torque to the frame is, we can work out the force to the frame. Remember the equation F is equal to torque divided by the distance. The distance in this case is the length of the torque arm, which is 0.175 meters long. D is equal to, and the torque is the value in this column. So in gear 1, F is going to be minus 10.05 divided by 0.175. So F is equal to minus 57.4 newtons. So we can put that into this column and populate the rest of the column. To convert force to the frame in newtons into kilos to populate this column, we simply divide this value by 10. Strictly it should be 9.81, but 10 will be good enough for us in this instance. So let's populate this column. You've probably noticed that the torque to the frame is negative in gears 1 to 10 and positive in gears 12 to 14. The reason for that is quite simple. In gears 1 to 10 we have a torque amplification going on inside the gearbox, and that means that the torque to the road is greater than the input torque to the hub of 3.89 Newton meters. So for the hub input torque to equal the hub output torque, the reactionary torque to the frame has to be negative. Where we have a speed amplification going on inside the gearbox, the torque to the road is less than the hub input torque. Therefore, the reactionary torque to the frame has to make up that difference. So in gears where we have a speed amplification, the torque to the frame is positive. In practice, these negative values mean the torque to the frame is in the opposite direction to the hub input torque. The hub input torque is always in a clockwise direction, so where we have negative torque to frame values, the reactionary torque to the frame is in an anti-clockwise direction. Now that we have all these numbers noted down and we understand what the negative values mean, we can go and test whether they're right on the bike setup that we have. I've added all the values that we calculated into this table, and as we go through the experiment we'll put the actual weight that we use on the torque arm in this column, and when we get to the end of the experiment we can compare the two. From around gear 8 to 14, the values are so low that it's going to be difficult for us to establish whether the weight on the crank is balanced by the weight on the torque arm. So I've calculated another set of values for the weight that we need on the torque arm, but this time using 10 kilos on the crank. So when we get to around gear 8, I'll add another 5 kilos to the crank to give us 10 kilos in total, and we'll populate this column and compare the values that we use to this column. We're in gear 1. The theoretical weight we need on the torque arm with 5 kilos on the crank is 5.74 kilos. I'm going to try 5.7. That seems to have balanced nicely. So in second gear, the theoretical weight that we want on the torque arm is 4.81 kilos. I'm going to go with 5. That seems to have balanced nicely. So in third gear, the theoretical weight is 3.95 kilos. I'm going to go with 4. That seems to be nicely balanced with 4 kilos. In fourth gear, the theoretical weight's 3.21 kilos. I'm going to go with 3.2. That's nicely balanced with 3.2 kilos. So in eighth gear, we're going to increase the weight on the crank to 10 kilos. And the theoretical weight we need on the torque arm is 2.07 kilos. So I'm going to go with 2. That seems to be nicely balanced with 2 kilos. 11th gear is direct drive, so there's no force going to the torque arm, so we don't need any weight on it. In gears 1 to 10, the torque was negative. That means it's in the opposite direction to the hub input torque. In gears 12, 13 and 14, the torque is positive, which means the torque going to the torque arm is in the same direction as the hub input torque. So that means we need to flip the torque arm around so that it's in the other orientation. In gear 12, the theoretical torque we need on the torque arm is 0.53 kilos. I'm going to use 0.5. Okay, that seems to be balanced with 0.5 kilos. In 14th gear, the theoretical weight we need on the torque arm is 1.41 kilos. I'm going to go with 1.5. Yeah, that seems to be balanced with 1.5 kilos. Comparing the theoretical weights with the actual weights, you can see that we're really very close with all of them. So I think we can have some confidence that our calculation is correct. Looking back at this chart that we put together with the torque to road and torque to frame values, if we divide each of these values by the hub input torque of 3.89 Newton meters, we'll get a torque to road value that is normalized to the hub input torque. We can do the same thing with the torque to frame values. This is a graph of the normalized torque to frame and torque to wheel values. On the x-axis we've got the internal gear ratio, and on the y-axis we've got the torque divided by the hub input torque. This red line is the hub input torque. And because on the y-axis we've got the torque divided by the hub input torque, the hub input torque is always 1 because it's the hub input torque divided by the hub input torque. This blue line is the bottom bracket input and output torque. Because that's 2, we know that the drive ratio between the chainring and the sprocket must be 2:1. So something like a 32-tooth chainring and a 16-tooth sprocket. Each of these points represents one of the gears within the hub. So there are 14 points on the torque to frame line and 14 points on the torque to wheel line. In gear 11, the internal gear ratio is 1. So the output torque to the wheel is 1 and the output torque to the frame is 0. In gears 1 to 10, there's a torque amplification. So the output torque to the wheel is greater than the hub input torque of 1. In gears 12 to 14, there's a speed amplification. So the output torque to the wheel is less than the hub input torque of 1. The hub input torque always has to equal the hub output torque. That means the sum of the torque to wheel and torque to frame values has to equal 1. It also means that when the output torque to the wheel is greater than 2, the output torque to the frame is greater than the hub input torque. And that occurs in gears 1 through 5. In all of the other gears, the output torque to the frame is less than the hub input torque. The last thing we're going to look at is what the maximum possible torque to frame value is. You can see from the graph that the maximum torque to frame value is 2.58 times the hub input torque, and the maximum torque to wheel value is 3.58 times the hub input torque. It's worth keeping these two values in mind because they'll come in handy when we're looking at the next problem. To work out what the maximum possible torque to frame value is, we need to understand what the limits are. And there are two possible limits: the maximum force that the rider can apply to the pedal, and the maximum hub output torque to wheel value that can occur before the front wheel will lift.